It starts high at gas or steam. It phase changes and condenses to liquid, and then phase changes and freezes to solid. Look at the number 4 we did on the previous sample of questions. Do you notice some similarities between that number 4 and the one I'm looking at right now? This number 4 in the heat of phase change section we did yesterday, right? We did Q1, Q2, Q3, Q2, Q4, and Q5. We did all those Qs and then we added them up. That was the beast problem, right? Is this one similar? What's different about it?
The ice and steam
Are just flipped, right? So instead of we in number 4 previously yesterday, we heated up from ice to steam. Today, this one is going from steam to ice. What's the only thing that's going to be different about this at the very, very end? The what? No, you're still making a sum. What do you say? But how do we denote heat being released? It's a negative sign. That's it. I'm not doing this problem. We did it yesterday. Do you understand? Are you picking up what I'm putting down? You did this problem yesterday. I'm not going to do it again because you did Q1 through 5, which was a lot. You had your kilojoules and you had your joules, and you converted all of them to joules, and we add them up. But yesterday's question said how much heat is required, meaning absorbed, meaning positive Q. This one is asking for the release stage of it, because it's releasing energy in order to freeze. And that means going from gas down to freezing or to solid is an exothermic process, meaning it has a negative heat associated with it. So the only thing that will be different is a negative sign. Okay? So think about what you've done, and then you can apply it. So what we need to finish up is the last flap of the foldable, which is thermochemical balance chemical equations. And then it's pretty short, about maybe 10 minutes, and then we'll go to our lab. So this is actually already, this information here is already on your papers that I gave you yesterday. It's the section right next to the lecture problems over here. We're going to go through a couple of these, and then in your foldable, what I want you guys to do actually before we move there, in your foldable, here's what I'd like for you to add. So you have your last flap. It's called Thermochem Balance Chemical Equations. And I just want you to make up a sample balance chemical equation. A yields to B. Got it? If I told you A yields to B, and I told you it was exothermic, so you're adding this in your flap of your foldable right now. I told you it was exothermic. What would the sign for the delta H be for this? A negative sign. So just write exothermic, and whenever we write the balance or thermochemistry or thermochemical equation, every single time you're going to have a BCE, balance chemical equation, and then additionally you're going to have a delta H just written out to the side of it. That's it. That's all I mean by thermochemical equation. And then separately, let's say we reverse the reaction. I'm taking B to A now. I'm just reacting, right? We're making this. There's some colorful paper running down below the table. And will you grab a piece for Noah, SJ, and Jackson, my Jackson guys? Grab 3 pieces. So if it's endothermic, what's happening to the sign? It's a positive sign, and it's endothermic. And that's it. We will actually draw a couple pictures in here after we watch the video, and then we'll add to our little foldable. But let's go ahead and jump to these questions first.
Is it a specific, like, are there specific numbers?
Yeah, and that's what I'm going to show you on this on the question set here versus on the foldable here. So on, oops. I'm super skilled here. I'm not sure what's going on. Okay. So here, tell me which of these are exothermic. Which equations are exothermic? Is the first one yes or no? Why do we change CS? Because you do see this negative here? Okay, that's an exothermic reaction. Second one, yes or no? No, it's endothermic. You see a positive sign. Next one. Yes. Next one, think first, and then you're going to add the sign. We're going from solid ammonia to liquid ammonia. So think about how do you get from a solid to a liquid? Endothermic, because you give the energy to the solid. So you put energy into the process from a low energy state solid to a high energy state liquid. That's endothermic. Next one. Why? Gas to liquid. The gases are crazy excited. Liquids are kind of chill. You got to release that energy to get it down to chill state. So that's going to be negative, and that's not a negative sign. That's just something's in the text there. So we can actually determine our own nature of exo or endo depending on the phase changes that we already know. So before we move on, these little delta H's are specific to the reaction, and instead of calling them like technically mole ratios, we call them just energy ratios. So what this is saying is there's 129 kilojoules absorbed for every 2 moles of, ooh, what's the name of that? Sodium, it's not acid. Sodium bicarbonate, right? Or sodium hydrogen carbonate is a really cheap way of saying it, but sodium bicarbonate is your intellectual way of saying it. So we're saying 129 kilojoules is absorbed for every 2 of these that are required. Do you see we just made a ratio? We just said 129 kilojoules is equivalent to reacting 2 moles of sodium bicarbonate. Well, if this is equivalent, I can make it like a fraction, like a conversion factor, and that's what we're going to do in number 1 right here. So question, how much heat? What am I looking for? What unit? Joules or kilojoules, right? So joules or kilojoules is my question. As gained or lost or gained from the decomposition of 0.25 moles of sodium bicarbonate. So before we move to actual calculations, I got 0.25 moles. Can you give me a guesstimate or maybe some math behind how much energy would be absorbed? Because I said 2 moles requires 129 kilojoules. What's the relationship? Say again? One more time? Yeah. Around 500, well, hold on. 2 moles requires 129, so I got 0.25. How much?
32.
Tell me what she did.
Well, that's 2, right? So you divide it by 2, which brings it down to like 65.
Okay.
1, and then you divide it by 4 at that point.
Because 0.25 is a fourth of a mole, right? So dividing by 2 divided by 4 is just dividing by 8, correct?
Yeah.
So an eighth of the energy. You know the relationship. You can do that in your head. But why necessarily do you need to do it in your head? You can do it through stoichiometry. Okay, so stoichiometry requires us to start off with our 0.25. And I know you can do the math, but I'm going to show you the setup because this is a tool for you to always use. And you can use it in non-chemistry examples, right? You can say, I need to feed 500 fifth graders some chocolate pudding. Each of them get 2 tablespoons. How much do I need? You know, that's basically what we do homework plans now with all the pudding. Oh, those of you who are here said you missed pudding. We had a little party without you. Okay, so now we have, this is our starting point. Back with me. Okay, write this down. This is our starting point. I want to get to energy. What's my conversion factor here? 129 kilojoules is required for every 2. See this ratio, this BCE has a 2 in it right here, so you got to follow what the BCE says. So that's 2 moles of sodium bicarbonate. And this is exactly what Brock just did in his head. He did 0.25 divided by 2, which is dividing by 8 basically, or an eighth of this. So can you guys actually tell me the answer for real this time? Calculate. What is it?
Well, I didn't do that, guys. 16. Yeah,
What is it?
16.125.
Okay.
I'm just assuming that divided by 8 though.
Yeah, that's basically what it is, but I'm showing you the stoichiometry setup as well. So that would be 266, so 16 kilojoules. There we go. So you can actually think about it, and it does make sense to you. And the moles cancel, and the kilojoules are left. Great. Let's go ahead and do number 2. Now, each of these BCEs are going to apply to a specific problem. So look at number 2, what BCE is what is actually important. According to the BCEs in your paper. The last one, right, because it's talking about liquid water. The only one with liquid water in it is the one I've given you here. And we just decided that it had a negative 40.7 kilojoules associated with it for every 1 mole of water, gas, or liquid, either one. So this ratio is 40.7 kilojoules per 1 mole of water. And that's our energy ratio or conversion factor we will use. So in this question, how many grams of liquid water? So question, grams of liquid water. Thank you for some, go ahead and catch up. Your lab is due today still, so I'd like for you to participate by writing down some examples. Chillin is not going to help you pass this class. Okay, how much heat, I'm sorry, I'm looking at number 3. How many grams of this liquid water will be formed from the addition or removal of 456 kilojoules of heat? So what do we want to start with? 456 kilojoules of heat. Okay, I have heat. I want to get rid of heat and convert it to what, possibly? Moles of H2O. What's that conversion? So 1 mole of water, which we got from the balanced chemical equation, is equivalent to, and I'm going to put that 40, I'm going to just put it as 40.7 kilojoules of energy. And I know it's released because it says it's exothermic. And so that's why it's like talking about the removal of energy. So I'm not going to put the negative in the problem, but we all talked about it being released. Okay, so we got our kilojoules converted to moles of water, and our last step would be what? Moles to grams, because the question was asking about grams again. Is anybody confused where I got this information? Is anybody confused? Okay, where do we get this information? The balanced chemical equation, that's right above it on your paper. I just don't have enough space on the board. It's right here. Boom. Okay. So, right, and 18 grams goes on top, 1 mole of water goes on bottom, and that's like 100, what is this, 190? 201, okay, grams. Great. Okay, and so this is stoichiometry again, but in reference to energy. Okay, let's do this last one. We won't go through 4, we'll just go through 3. In this example, read it first. Tell me what's the equation is going to be in for number 3. The third one with the sodium hydroxide. And notice that this one's just, it says delta H of solution over here. So back up here, this is delta H of solution, which is just basically dropping some sodium hydroxide in water, letting it dissolve. It's not like a reaction, it's more just a solution process. So the sodium hydroxide goes from solid to aqueous form, and it releases 445 kilojoules of energy. That's so if I'm holding that beaker and that's happening, what does it feel like? It's gonna get hot, right? It's gonna get really warm, and I've done this before, and I almost burned myself doing this, but it gets very hot. Okay, so first question is gonna ask one thing, and second question is gonna be something totally different. Let's just tackle the first one. How much energy or how much heat is released? So what unit am I looking for? Joules, right? So the question again is joules or kilojoules. It's helpful to write that so you don't forget what unit you're looking for. By dissolving 42.3 grams of sodium hydroxide in water. What do I start with? The given, so 42.3 grams of sodium hydroxide. What's probably our natural first step here? Right, because you can't do much with grams. And that number given to you above, that 445 kilojoules, what's that per? Per what? 1 mole, because in the ratio, or in the BC, it says 1 mole of sodium hydroxide. So I need to convert this. 1 mole of sodium hydroxide weighs, I think, 40 grams. 40 grams? Okay, thanks. It was rounding these again. So now we can convert to moles. We're in a good place when we get to energy now. What was that number that related its energy ratio?
So that's when you
I'm taking the negative out because I'm just going to say this energy is released because that's what the negative is signifying. And that's 445.1 kilojoules of energy per 1 mole of sodium hydroxide. That's in this reaction here. And that's just based on the VC. So our grams cancel, our moles cancel, and go ahead and calculate. It's going to be like, yeah, the NaOH goes. It's just me labeling 100% for you. So it's going to be like 450. What is it? What is it? 470? Okay, so 471, I'm going to round up. Okay, so if this amount of energy is released and as the solution process occurs, we need to use that information to answer part 2. So question, how much would this heat change? So this heat change here, this is Q. Change the temperature, so what's it asking for? So delta T, right? It's asking for delta T of 1 liter of water. Okay, so again, we have a Q, we have the energy, we are asking for delta T, and it's giving you a liter of water. What equation can we use for the second part? We have to use Q because right, because it's the only one with the delta T in it, first of all. But what's the M? No, it's talking about water. If you were using Q equals MCAT and you're looking for a temperature change of water, you better be using water for every single variable possible. Say again? Where are you getting 1,000 grams from? Right, 1 liter of water is how many milliliters of water? 1,000 milliliters of water, and 1,000 milliliters of water is 1,000 grams of water. You don't even need to show your work for that for me. I'm cool with you doing that part in your head. So in terms of the information given, Q equals MCAT is what I'm hearing. I'm looking for delta T, so what do I divide by? If not math, it's just MC, right? Divided by MC, so they cancel on that side. So delta T is equal to Q over M and C. Okay, what's Q in our problem? 471 kilojoules, right? Well, what's the C value? Always published, usually joules, maybe some calories every now and then, but joules, right? So I need to convert this to joules first. Can you do that in your head? How many joules is that? 471,000 joules, because it's 1,000 joules in 1 kilojoule, divided by, what was the mass Luke said? 1,000 grams, which was our 1 liter of water. And what's the specific heat capacity of water? 4.18 joules per gram degree C. And so every unit cancels except for what? Celsius, right? So joules top and bottom cancel, grams top and barely here, but bottom cancel. Celsius is the only thing left, so this will be like 113 degrees C. Ooh, doggies, right? If I'm holding that beaker as I'm mixing this sodium hydroxide, all the energy is being transferred to the water. Well, good thing I have a liter of water because it will dissipate the heat around, 1 liter, but that baby gets hot. So I usually have to use like oven mitts to mix that when I make solutions for real flowers. But that's combining both heat transfer and thermochemical equations. What's up? Emily, you have a question? Yeah. That's one that's in your head. You wrote it down in your web quest. The C value for water is 4.18 joules per gram degree C. We'll use that a lot. So write it in your foldable if you need to help remember it. Okay, guys, what about piece of paper? Let's talk about the lab. The lab is very easy. You have a little less than an hour to do it. I'm going to leave that up there for a minute. I think it's working still. It's called the Heat Diffusion Lab. Heat Diffusion Lab. So you guys are going to get 45, because the last class only took about 30, so I'm going to give you guys a little more. So my 2 tips for you are in the reading on the very first page. Take about 5 minutes of your group and read through it. And if you see anything that's important, jot it down as a given for the very beginning of your lab, or after your purpose statement, of course. When you're doing the lab, a lot of you start reading, I'm going to warm up water. I have to warm up water to about 50 degrees Celsius. It says to use the hot plate. This will take way too long on hot plate. I'll warm it up in the microwave for you. And then I'll come around, so just have a graduate cylinder, a 100 milliliter graduate cylinder at your lab station so I can quickly pour it in there. And then from there, just follow the lab to the T, and you guys will be fine. And remember in labs, you always use your data to answer your questions. Don't try to always think back to what we talked about in lecture or what we've done in comments before. Use your data to calculate anything that's asked of you. It's like number 5 on the first set of questions. That's what makes me like, how do I do this? Use your data. Okay? Groups of 3, Heat Diffusion Lab. I'll bring around some of the topics of teal time. Give me broke some stuff. What? We let you know after. So please come over here. Grab a sheet. The ice is in here whenever you need it later in the lab.
They just kept good stuff. Color.
Again, this lab is due at the end of class, so thank you for using your time wisely. Okay, warm water coming through. Oh, I need a campaign. that I give you, and then I'll screen it. So very clean. Well, you can that's right. Right now. I am coming around. This is how you speak immediately. You need to start. You have a lot of air in your lap. You don't need any. I'm already giving you 75 milliliters, so I'm not sure what else you need. You need to have somebody managing the lab instructions to make sure all the group members are participating. No, I mean, I just wanted to know. So I don't know. Maynard does it. Put your lid on because you're going to have error in your measurement. Your heat is escaping. It's not ready. All of your 75. The guys out. Alright, your body temperature is normally going to be between 4 and 8 degrees Celsius. Once you hit that, you can stop collecting data and start calculating. I need all hands on deck. If not, I'm going to start docking participation bonus.